Okay, so over the course of Chem 20 and Chem 30, we've been learning a lot about acids and bases. And one definition that we've used to describe acids, for example, is that it's a compound that contains hydrogen. Or, as we kind of explored a little bit more in the modified Arrhenius theory, it's a compound that will make hydronium in solution, hydronium ions. And so HCO3 minus, we look at that and we kind of say, okay, yeah, that's an acid because it contains H plus in it. But turns out that if I take this hydrogen carbonate solution and I do a litmus test on it, you can see that the litmus test turns out blue. And so this definition for this compound of being an acid kind of breaks down for us a little bit. And so what we're going to learn about is a new theory called Bronsted-Lowry Theory. And this theory is really good in that it helps explain a few deficiencies in the Arrhenius theory and why we see certain things that we see in chemical reactions. It's not a theory that we really use to predict what's going to happen. It's more of a theory that we use to explain things that we are seeing in chemical reactions. So there's two definitions that you need to know for the Bronsted-Lowry theory, and it's the definition that it has for an acid and a base. You can see them up here on the board. An acid is simply put a proton donor. Now, proton meaning an H plus ion. A base is a proton acceptor. So if we have a chemical reaction like this one where we've got hydrochloric acid reacting with water, you can see in this chemical reaction that in order to produce hydronium and chloride ions, the hydrochloric acid has to donate a proton to the water molecule. That means that this is the proton donator or donor, this is the proton acceptor, and so this is my Bronsted-Lowry acid, the hydrochloric acid, and the water is my Bronsted-Lowry base. And yeah, it's kind of weird to call water a base, but under that definition, that's what we call it. Now you can also see over here on the other side, I've labeled this as Ca and Cb. And all this means is that this is my conjugate acid and my conjugate base. Now you can see that hydronium was produced as a direct result of water accepting the proton from the hydrochloric acid. So this base turns into an acid now type of compound. And so we call it a conjugate acid. Conjugate, or to conjugate, if you've ever taken a Spanish class or a French class, when you conjugate verbs, you're just changing the verbs from one form to another. So this has been changed into an acid, so we call it a conjugate acid. And so this base turned into the conjugate acid, so we call that a conjugate pair. Also, this acid turned into this conjugate base, and so we call this a conjugate pair. So Bronsted-Lowry equations have two pairs in them. One acid conjugate base pair and one base conjugate acid pair. The tendency that I find that kids love to do with this concept is they like to pair up when they're asked what's the conjugate pair, they like to say, well, the acid and the conjugate acid is the pair. And that's not the case, okay? The pair is, what did this substance come from? HCl and Cl minus are related in that Cl minus came from this compound, so that's the pair. Water and hydronium are related because hydronium was formed due to water accepting the proton. And so that's the pair. So that's how you got to think about it. In this second example, again, it's just really the same thing, but you can kind of see the reverses happening. Here, ammonia is accepting a proton from water. And so that now makes, in this reaction, water a Bronsted-Lowry acid. And it makes ammonia the Bronsted-Lowry base. And because ammonia becomes or accepts a proton, it now becomes NH4 positive, which makes it the conjugate acid. And these two things are the conjugate pair. Water, because it donated a proton, became OH minus, hydroxide ion. And so this is the conjugate base. And this acid conjugate base relationship is the conjugate pair for those two. And so that's what you need to know as it relates to that. Now, you might be asking yourself, well, okay, so acid is acting as a base or water is acting as an acid and a base. What does that mean? All that means is that there are some substances out there in Bronsted-Lowry theory that can act as both, depending on the situation it's in. As you can see for water, two different scenarios, two different definitions. depending on the situation it's in, it can either act as a proton donor or it can act as a proton acceptor. And if you have a substance that has that ability, like water does, then we classify that substance as an amphiprotic substance or an amphiprotic species. And it just means that it has the ability to act as a Bronsted-Lowry acid or a Bronsted-Lowry base, depending on the situation that it's in. Another thing that I want to point out with these two reactions is anytime that you see an arrow just pointing straight one direction, then obviously all of these reactants are going to turn into all of these products. But anytime that you see these equilibrium signs here, where we've got kind of a weak acid reacting with a weak base, these equilibriums are established. And again, because it's an equilibrium, it's got a K value, an equilibrium constant. And so one way to know whether the reactants or the products are favored is if we know what that equilibrium constant number is. If it's greater than 1, then the products are favored. If it's less than 1, then the reactants are favored. We know this and we've learned this. But if we're not given the K value in reactions like this, we can still determine whether the reaction is favoring the products or it's favoring the reactants. And the way that we can do that is with our data booklet and this acid-base chart. So if you take a look on your acid-base chart at these two substances, so ammonia and water, and you find them in here, ammonia is a base, so you can look at it in the conjugate base column of the booklet. You find it in the booklet here, and it's right here. So you stick your finger on it, and then you can find water in the acid column, which is way down here at the bottom. It's the weakest acid of them all, which makes sense. You can see that my right finger is above my left finger, kind of like how we did it in the redox unit, where my right finger over my left finger. And this means something. If I have an acid-base relationship in a Bronsted-Lowry equation like this, where my right finger, my base, is above my acid, my left finger, then that means that the reactants are favored. And so I can write this down kind of like this. So my reactants are favored in this case. Now I can also have my acid above my base. And if that's the case on the chart, then all that means is that my products are favored. And so if I had like a really strong acid, where my strong acids are found way up here, I had a pretty strong acid, like let's say H2SO3. It's not a strong acid, but it's a strong weak acid. I had that acid reacting with this pretty strong weak base, which is CO3 2-, then you would expect that reaction to have the products heavily favored, and you would see that in a equilibrium constant calculation if you were able to do it. But we can use this chart to determine whether a Bronsted-Lowry equation favors the reactants or the products simply by using this rule. And that's it. So I'll be right back with another clip and another concept as it relates to KAs and KBs. So I'll be right back. What we're going to be looking at here is your acid-base chart in your data booklet. Now, your data booklet is a lot bigger of a chart than what I've got up here on the board. Up here on the board is just a select few acids and bases with the Ka values up here on the board. But what you can see is that I've still maintained the order. So you can find hydrochloric acid up near the top, and then oxalic acid is below it, and then hydrofluoric acid is below that and below these. And all the orders have been maintained. And so the reason I've done that is so I can show you the trends that are visible on this chart. So the first thing that I want to point out is that on that chart at the very top, those first 6, those are the strong acids. Those guys 100% ionize. And so you might see the Ka value and it says very large, and you wonder, well, why doesn't it have an actual number there? And the reason why is because if we were to write the Ka expression for a strong acid, if you think about it, at 100% ionizes, which means basically all the reactants are going to turn into all the products. And so my Ka value here, I'm going to have a very large concentration, or a very large number due to the multiplication of the concentration of all the products that ends up on the numerator, and a very small number for the reactants on the denominator. And so when I take a really large number and divide it by a really small number, I just get a very large number. And so that's why they put very large in there for all of the strong acids. It's just as a reminder, hey, this 100% ionizes. It's really not an equilibrium reaction, and so it's just very large. It's a quantitative reaction that you can do stoichiometry with. Down here at the bottom on the left-hand side are the weakest acids. So if you look on your chart, you'll notice at the very, very bottom of the acid chart, the acid column, water is the weakest acid. And that makes sense. And then over here, this is the conjugate base column. These are just the bases that you would find in this acid-base chart. And what you'll notice is over here on the bottom right-hand side, and I didn't write it on this chart, but you'll notice on the bottom right-hand side in the base column is hydroxide, OH minus. And hydroxide is the only strong base. That's it. And every other base that is above it is going to be weaker than hydroxide. So our strongest bases are down here in the bottom right-hand corner, and our weakest bases are up in the top right-hand corner. Now you'll notice these Ka values are written in for some of these acids, and I just copied these out of the data booklet, so you've got them and they're there. But this is one column that I wish they would add to this chart, and they don't do it. And I think it's mainly because they want you to know how the chart functions and how to calculate them and whatnot. But this is what I think an ideal chart would look like, is I've got the Ka value here and I've got the Kb value over here. Now how do these numbers apply and how do I get them? Well, I've tried to color code this as best as I possibly can in terms of putting the acids in black ink and the bases in blue ink. And so these Kas obviously apply to the acids. It's an equilibrium constant for acids, and so this makes sense. All of these Ka values is for the acid in the corresponding row. So oxalic acid, HOOCCOOH, its Ka value is 5.6 times 10 to the negative 2. And for hydrofluoric acid, its Ka value is 6.3 times 10 to the negative 4. What I want you to notice and make note of is that you'll notice that as I move down the chart, the weaker the acid I become, the smaller my Ka value becomes. Which also makes sense, right? If I'm starting up here very large with strong acids and I'm getting weaker acids, it would make sense that my Ka values get really small as I get really close to the bottom of the chart. But these Kb values here is where kids sometimes get a little confused. So I can calculate a Kb value by using this formula that we talked about in one of my previous videos. Ka times Kb equals Kw. And I know what Kw is. It's 1 times 10 to the negative 14. And if I have the Ka value for a particular acid, I can also calculate the Kb value of its conjugate base. And so I can just rearrange this formula like this, and you can check my calculations for me to make sure that I'm correct. But if I've done them right, this is what these numbers punch out as. And again, I wanted to point out that if my strong bases are down here in the bottom right-hand corner, I would then expect my Kb values to be fairly high. And then as I'm getting or using or looking at weaker bases, my Kb values would trend to be smaller. And this is the case. You would see this if you were to calculate all the Kbs for every conjugate base on the chart. You would see that trend where as you move up the chart, the Kbs get smaller. And so these are two important trends that you need to be able to identify and know, and I would make note of them in your data booklet so that you've got them. And so just to point out, these Kas apply to these acids here, and these Kbs apply to these conjugate bases. Now, for substances that are amphiprotic, like HCO3 minus that we had been talking about in the previous video, you can see that HCO3 minus is here in the chart, and it's also here in the chart. It can act as a base or it can act as an acid. And so when we did that litmus test, I showed, okay, well, and when I did this litmus test with hydrogen carbonate solution, it turned out blue. And so how does Bronsted-Lowry theory explain this? Turns out that we weren't really wrong in saying that HCO3 minus is an acid. It can act as an acid. It does have a hydrogen that it could donate to another substance if it wanted to, given the right circumstance. But if HCO3 minus, the hydrogen carbonate ion, has a choice of whether it's going to donate or accept a proton, then it's going to do what it is stronger at doing. And so if you're to compare the Ka of HCO3 minus, which is 4.7 times 10 to the negative 11, and the Kb of HCO3 minus, which is 2.2 times 10 to the negative 8, you can see that its Kb is a larger number than its Ka. And so its tendency, when given the choice, is going to act as a base. So with water, for example, it has the choice to choose, okay, am I going to donate or accept? And it's going to accept a proton from water and make those hydroxide ions in solution. So one common mistake that kids make with this is when I ask them, okay, what's the Ka of and the Kb of an amphiprotic substance? They'll say, okay, well, here's the Ka, and so it's 4.7 times 10 to the negative 11. Then they'll use this formula with this number, and they'll calculate that, and then they'll think that this is the Kb of HCO3 minus. But remember, this Kb is the Kb of CO3 2 minus. So you have to go to where this substance is found in the chart, use the Ka of its acid form in this formula to calculate its Kb for that substance. And that's how you calculate Kas and Kbs for particular substances. And that's how that chart is set up. So if you've got questions, let me know. But that's all I've got for this one. I'll be right back with one more example as it relates to Bronsted-Lowry theory and how you can write these equations. This last concept of predicting and writing Bronsted-Lowry equations or reactions is what we need to cover for this theory, and then we're all done. So what you'll see is sometimes just some word problems, and this is very similar to writing and balancing redox reactions from our redox unit that we did, where you just have to kind of identify what's in the solution, what's present, and then identify what are the things that are going to actually undergo a reaction together, and then predict what those products are going to be. So here's the rules that I've listed for you in order to be able to write and predict these Bronsted-Lowry equations. And the first one is just simply list the species present. So here's my first problem. I've got what reaction occurs when vinegar is used to neutralize spilled drain cleaner, which is composed of sodium hydroxide. And so I'm just going to list out the species present. Now, one thing that I need to point out as it relates to listing the species present. If you have a weak acid in your list of species present, then you just write the weak acid as is. So CH3COOH. If I have a strong acid, then you need to write the strong acid as H3O positive, hydronium, and then its anion that it's made out of. And that's because strong acids 100% ionize when you put them into solution, and so those are the species that are going to be actually present, not the strong acid molecule itself. Whereas a weak acid, it ionizes much less than 1%, and so because of that, we're going to write what's predominantly there. In this case, the weak acid CH3COOH vinegar is going to be written down. So there we go. Here's my species listed. I'm obviously going to include water in that because these are solutions. And then sodium hydroxide is an ionic compound that's soluble in water, so I just write it as its ions, Na plus and OH minus. The next rule here is you just in your data booklet, in the acid-base chart, you look on the chart for, on your species listed here, which one is considered to be the strongest acid that's present. Now, this is vinegar. It is a weak acid. It is not a strong acid, but on this list, vinegar is the strongest acid using this chart of what I have. So I list that as my strongest acid. I also identify hydroxide as my strongest base. And then the last rule is you just react the two together, the strongest acid with the strongest base in a Bronsted-Lowry equation or reaction. And so I've done that. I've got the vinegar plus the hydroxide, and because this is my Bronsted-Lowry acid, I know that this is my proton donor. This is my Bronsted-Lowry base, so I know that this is my proton acceptor. So I'm just going to donate the proton. You don't have to draw the arrows in if you don't want. I like to. It's just a good visualization of what's transferring from one molecule to the other. And so this helps me now write out what my products are over here on this side. So this CH3COOH is losing an H positive, which means it's going to become the acetate ion. And this OH minus is gaining an H plus, which means it's going to become HOH, or in other words, just water. And so there's my equation, and that's all you really got to do. Here's another quick practice problem that we can do together. It's perchloric acid is used to neutralize an ammonia solution. And so this perchloric acid is a strong acid. It's one of the 6 strong acids on the chart. And so as noted here in the notes, you need to write strong acids as H3O plus and its anion. So I've done that. You can see I've got H3O positive here and the chlorate ion that it is made from. It's also a solution, so I know the water is present, and then I've got my ammonia as an aqueous substance there as well. I identify using the data booklet and my acid-base chart which one is my strongest acid and my strongest base. The most common mistake I find that kids make here is when they list their species present, they write actually perchloric acid, so HClO4, and then they try to use HClO4 in their equation, and then it messes things up, and they don't actually get the right equation. So because we're not writing HClO4, that's not an option when you're selecting your strongest acid. Your strongest acid is going to be just the hydronium ion, and my strongest base in this one is going to be my ammonia molecule. So I react them together. Again, this is my acid, this is my base, proton donor, proton acceptor, and so I can just draw that in like that. And this becomes H2O, it loses an H plus, and this becomes NH4 positive. And that's it. That's all you got to do, guys. It's that simple. One thing that you can do that would be good practice for you, you can pause this video, and on these 2 reactions here, I want you to identify 2 things. First of all, I want you to identify, in addition to what I've identified here is your acid and base, I want you to identify what's your conjugate acid and your conjugate base. Also, for both reactions, identify what are the 2 conjugate pairs that exist. And then finally, you can also, for both reactions, using your data booklet and the acid-base chart, identify which reactions are favoring the products or reactants. Do they favor the products? Do they favor the reactants? You can use the finger rule as we described before in a previous video and make that determination. So good luck, guys. Thanks for watching, and we'll see you with the next video shortly.